Hi there, welcome back to the breadboard. In this episode, we're going to look at upgrading some 3D printers. You've seen the reviews, hopefully, of the last couple of 3D printers that I've built. And one of the things that comes up is that the Tronxy X5S cannot get a good enough bed temperature because it is a very large bed and is running on 12 volts. So what we're going to look at is upgrading it to a 24 volt system. Gearbest has worked with me and sent me some parts to try and do this, but one of the things I want to have a talk about before we actually do the upgrade are external MOSFETs. We need to use one to do this upgrade, but there seems to be a little bit of confusion about what exactly they are and how you wire them up and things like that, and what do they do for you. You can, even without doing a 24 volt upgrade from 12, an external MOSFET can even help you get better performance out of the bed that you already have running at 12 volts. So let's get to the bench, have a look at an external MOSFET, and also one that's built onto a main controller. I've got a RAMPS 1.4 board as an example, but it's pretty typical of most. And then we'll have a look at some data sheets, and I'll explain to you how and why a MOSFET will do what it's going to do for us. And we'll look at the schematic of a typical external MOSFET driver, in fact a couple of them. And then we will, in the next video, go ahead and actually do the full upgrade on my Tronxy X5S to take it up to 24 volts and wire in the external MOSFET. What we will also look in this one too is the wiring, because along with upping a 3D printer to use 24 volts, when you do this, if you don't change anything else, you will have issues with massive increases in current draw through cabling and things like that. So we want to talk about what you should and shouldn't apply the 24 volts to. So for this video on its own, we're going to talk about the external MOSFET, and then in a separate video we'll talk about the wiring and how you can improve that, and how you would connect everything in, and then subsequent to that we'll actually go and do it for real. So without further ado, let's get to the bench and have a look at what we're actually talking about. Okay, so we're looking at a bunch of different pieces here that we would potentially change if you want to upgrade our 3D printer to use 24 volts. This item here is the external MOSFET, so that's the one we're going to have a close look at. The other items here are things like the hot end heater. This is a 24 volt one. The one that's in this standard E3D clone is a 12 volt one, so obviously you can't just bang 24 volts into that without doing anything else and expect it to work properly. You may damage it and overheat and things like that. This is a separate controller. This is the 4988. I'll put the part number up, as opposed to the TI one, so we'll have a look in another video about those. This is the RAMPS 1.4 board, and the MOSFETs that are built onto them are these three here. One is for the heat bed, one is for the hot end, and one can be used for a fan or a second hot end. So you would have two extruders, and this board actually supports two extruders. You've got X, Y, Z, extruder 1 and extruder 2. So you could do that with the RAMPS 1.4. Anyway, the one we're interested in is this particular MOSFET here. And you notice there's no heatsink on it. All it is a basically it just looks like a transistor, because that's what a MOSFET is. It's just a metal oxide silicone field effect transistor. And this one here is soldered directly into the board. There's no heatsink, so if you put too much current through it, it will get pretty hot. But there are other issues that we're going to talk about. If you look at the external MOSFET, you can see here it's a much bigger MOSFET. It's got quite a big heatsink on it. And what I want to do before we get into the schematics is quickly look at the data sheet for these two different MOSFETs, because it will actually make a difference as to what MOSFET you use. Now, these external ones tend to have much better MOSFETs on them than, say, a RAMPS 1.4 typically would have. And that's one of the reasons why, when we talk about it, that you will get better results even if you don't up the power supply to a 24 volt one. by using an external MOSFET. The other thing that is really important is wiring, and you should really upgrade to something like 12 gauge wire if you're going to go up to 24 volts as well. And even if you don't, increasing the wire, especially if you've only got something like 18 or 20 or worse, 24 gauge wire running to your heat bed, then thickening up the wire will help. Now I'm talking about the copper, not the plastic, of course, because you'll get less voltage drop across it. I'll talk about that later. So anyway, let's go look at the data sheet for these two MOSFETs. Okay, so the first MOSFET we're looking at is the one that is on the RAMPS 1.4 board. The reason we're doing this one first is because I want you to understand why we would get an improvement going to an external one. So the one we have that is typical on these, and if you look up the RAMPS 1.4 schematics, it will also show up using this device, is an STB55NF06. And the kind we have is in a TO220 package right here. So it's a 60 volt, 50 amp MOSFET. That means that it will be able to work with a supply up to 60 volts and up to 50 amps, but not 50 times 50 amps at 60 volts. It won't be able to do both of those because it'll just, it wouldn't be able to dissipate the heat. But if you're using the MOSFET as a switch, i.e. you're either fully turned on or fully turned off, then you can go up to a considerable amount of current through it, providing you are able to dissipate the heat. Now, the heat or the power that this thing is going to dissipate is going to be based on this figure here, where it says 0.015 ohms. That is 15 milliohms. That is its resistance when it is turned fully on. And I can't stress this enough, fully on, because one of the parameters, and I won't try not to get too technical on here, which is called gate threshold voltage. So VGSTH, the gate threshold voltage, is 3 to 4 volts. So typical about 3 volts, maybe 4. But this is where it's starting to turn on. It's not when it's fully on. It's the threshold where the MOSFET will start to turn on. Now consider that this is being driven by a an ATmega 2560 microcontroller or something similar to that. So it at best is going to run on 5 volt supply, which means that the digital outputs are going to be a little less than 5, maybe nearer 4 volts to 4.5 volts. So you're really sitting in the realms of not necessarily saturating the MOSFET to its full on condition. So RDS on, a different parameter for its on and off states. Static drain source on resistance. So it's saying here the 15 milliohms to 18 milliohms is when the gate source voltage, which is the one that we looked at before that was saying about 3 to 4, is sitting at 10 volts. Now at this point it can also be having up to 27.5 amps through it, but you're looking at the on resistance there being about 15 milliohms. So when you're only driving it by 4 or 5 volts, you may be 20 or even more milliohms in here, which means using Ohm's law, you've got I equals V, which is your volts, over R, which is your resistance. So I, it may be 10 amps or 20 amps depending on your heat bed, and the current because you're feeding it from say 12 volts. So let's just say it's 10 amps, we'll keep it simple. So if you've got 10 amps and you've got 15 milliohms, that means that you've got 150 millivolts drop across the MOSFET. All right? Now that doesn't sound a lot, but it's at 10 amps. That's 1.5 watts. That MOSFET, even at 10 amps in this state, when it's fully turned on, or when it's turned on, here, is going to be dissipating close to 2 watts. So that's a lot of heat, and as you notice here, there is no heatsink on this. So it's going to get hot, probably hot enough that you can't touch it. If you're unlucky and you're drawing a bit more than that, then you could end up having it thermally running away or burning out or something like that. You've also only got an 11 amp fuse on here. This other one here, these other two poly fuses, this one is for controlling everything else. This one is an 11 amp one for driving the heat bed. So you couldn't draw more than about 10 amps without this thing starting to shut down the current anyway. But this thing with 10 amps is going to be dissipating close to a couple of watts. I have a table that I'll put up here that shows you for this MOSFET and also the other one. Now, so we looked at a couple of parameters there. I don't want to get, as I said, don't want to get too complicated, but the MOSFET won't turn on until it's being driven by 3 to 4 volts at least. This is typical, so maximum could be as high as 0.4 volts. So the ATmega, the controller on here, with all the connections and various other things, it's only just going to be turning it on. So your resistance may not be as low as as you think from the data sheet. So you're going to be dissipating a couple of watts of heat at least. When you increase your voltage, say to 24 volts, if you're talking about increasing voltages, then you're going to quadruple the power, because if your heat bed, let's just say it's 1.2 ohms, keep the math simple. 1.2 ohms with 10 amps, that's 12 volts on the heat bed, that's 120 watts. If you go up to 24 volts, you're going to double the current to 20 amps, and that's going to be from 120, it's going to be 480 watts, because the power is I squared R. So if you've got 20 squared, that's 400 times the resistance. So you're going to have 480 watts on the heat bed, but you're also going to have about 8 watts or more, about 8 watts on this MOSFET. That's definitely going to burn it up. Now, let's look at the other MOSFET that we use on this external MOSFET controller. So this is the one that's literally is this one that's on here. This one has an RDS on of only 3 milliohms. So it is 4 times less resistance. It also will work up to 80 volts and up to 200 amps. So it's a far, far more powerful MOSFET. But the key things that we want to look at here is it's 3 milliohms when the gate source is at 10 volts. So the same thing. This one was 15 milliohms when the gate source voltage was at 10 volts. You're never going to get that from a microcontroller. Not one of these microcontrollers that do this anyway. This one is also specified at 10 volts, which is 3 milliohms. But the difference is this one is going to be driven by the output of this one. So even if this doesn't turn fully on, it's still going to be outputting 12 volts. So this is going to have more than enough voltage. A MOSFET is not a current amplifier. You can think of it as a voltage controlled resistor. When you put enough volts on the gate, it will turn fully on. Because we're getting 12 volts out of here to drive this one, when we wire it up, this will be turned fully on, and we will get about the 3 milliohm, which means that our at 10 amps, that means it's only going to be dropping 30 millivolts, and the power dissipation is only going to be about 0.3 of a watt, far, far less than this. So even without a heatsink, this thing would be just fine at 10 amps. Even at 20 amps, it's only going to be dissipating a little bit more than sort of 1 or 2 watts. I'll put the table up again here so you can see. So having a little heatsink on this is more than enough. So you can see now almost immediately that you're losing 2 watts odd, or sorry, as much as 8 watts if you're trying to do 20 amps on here. When you're trying to turn this on, 8 watts is maybe 10% of your heat bed power. This one, far, far less. You're allowing more voltage to get to your heat bed. Right? And this is going to run cooler. So can you run this one on 24 volts without doing anything else? Yes, you can. The Ramps 1.4 board actually has 2 inputs. One of them is for the heat bed, and it only links through the poly fuse to here. So obviously if you go up to 24 volts on this, and you're drawing closer to 20 amps or 15-20 amps, this fuse is no good. You'll have to cut this out and put a 25 amp fuse in there or something else, or even just short it out and don't even have it. The other side, which drives the board and the Arduino that this would plug into, would still be using the 12 volts going into the end, and that would still be just fine. So the 24 volts could be fed into here for your hot end, but the power being dissipated on this MOSFET would probably destroy it. Unless you had a heat bed similar to what is on the Chivo Black Widow, for instance, which is the 24 volt heat bed, it doesn't draw any more current than the 12 volt heat bed on a Tronxy X5S, because it's a higher resistance. It's designed to work with 24 volts. It's about 300 watts, and it draws a little bit over, I think, 12 amps or so. Again, I got a table here, show you. So in summary, what does an external MOSFET do for you? Well, it allows you to get more power delivered to your heat bed. It allows you to easily run 24 volts without having to modify this. And because it's being driven by a higher voltage, it will turn fully on and drop even less volts across it when you're trying to work your 24 volts, and you won't generate anywhere near as much heat. So what else do you need to know about these external MOSFETs? You have a connection that goes to your control board. Now this particular one came from GearBest. They sent it to me specifically for doing this video and to do the upgrade, so I can show people how to do it. This one has a full bridge rectifier here. And what that means is that it doesn't matter which way around you connect these wires in. So no worries there, because it will correct any errors in your wiring for the signal wire from the controller. Not all of them are like that. The bigger one with the red heatsink, there's a picture of it. I don't have one. Well, there's one on my Black Widow, and I'll put a picture up, but I don't have it in my hand here to show you. It doesn't have a rectifier, so you have to pay attention to connecting this the right way around. The next thing you've got over here is an opto-isolator. That means that your 24 volt power supply and the heat bed is completely isolated, or can be, from the rest of your controller. So it doesn't matter what happens to it electrically, it's not going to fry anything here, your displays, your controller that this is working with, or anything. It's completely isolated, and I'm going to put up a diagram in a moment so that you can see that. So you've got full wave rectification, which means it doesn't matter which way around you connect this to your controller board, it'll work either way. And you've got an opto-isolator, which means you've got several thousand volts of isolation between your 24 volt system and your 12 volt system. So that's a level of safety, if you like, protecting your system. The other part of this is you've got your DC in, so you put 24 volts on here. Pay attention to the polarities though, the MOSFET does care. So you've got 24 volts in, plus, minus, and then your heat bed goes on here. Now it just says hot bed, that's all it says, because the bed itself is purely a resistor. It does not care whether you connect the plus and minus or they're swapped. So you just put your heat bed on here, your power supply on here, it's completely isolated, your signal from your controller onto here, and you're done. When you apply volts to here, it's going to be about 12 volts in our case, then this MOSFET will get turned fully on, and the 24 volts gets connected to the heat bed, and away you go. The red one does not have the full wave rectifier, so it does care, but it does have the opto isolator, and there's a couple of other components to drive the MOSFET probably a little harder, but basically it's just the same thing. It's just a little beefier, and it cares about the input polarity, so you need to pay attention to that one when you're wiring it up. Outside of that, either one of these is going to do for pretty much any of the 24 volt heat beds that most of us are going to be using. This one is cheaper than the red one, but it's still way more than adequate to drive it. And I like the fact that it's got the rectifier on the inputs, which means you don't, for somebody that's not into electronics much or doesn't have a multimeter, it doesn't matter which way around they connect this. Not all heat bed controller outputs will be marked for plus and minus. The RAMPS 1.4 board does have it plus marked for each of the outputs, but not all controllers will necessarily do that. So the principle of this is exactly the same. All right. So a few things about the MOSFET. All right. It's not a solid state relay. A solid state relay looks like this. So that is a solid state relay. What you have is you have a control input, which, like the MOSFET, can be up to 20, in this case 16 volts, but you can get different voltage inputs, 4 to 16 volts control. You can get some that work with lower voltages, so they work easily with microcontrollers. But the output is more like a relay. It's solid state in this case, but it switches AC. If you put 24 volts DC through a load like a heat bed into here and then to ground, you could turn this on, but it would never turn off. All right, these use what's inside a thing called a triac, and what they do is they get turned on, but they rely on AC of the mains going through 0 volts to turn off. If it never goes through 0 volts, it won't turn off again. So a MOSFET is not a solid state relay. What a MOSFET is the simplest way of describing it is it's a voltage controlled resistor. These are linear devices, although some of the ones that you get are more specialized towards switching applications. So their linear region is less defined, and the full-on, full-off area is emphasized in its characteristics. And that's what these ones are. They're more for switching applications like power supplies and stuff like that. But they can be worked in a linear region too, which is why in the case of the RAMPS board, this one, because it's not getting turned on as hard, will get hotter because it's not getting as lower resistance across the source and drain, which are the 2 pins of a MOSFET. So it drops more voltage, and at the high currents it generates more heat. Because you're driving this one with the 12 volts, it's not going to get as hot. I know I've said that a couple of times, but I need to emphasize that. Now, if you're using a heat bed that's 12 volts, you can see already that you can actually get an extra couple of, an extra watt or two to your heat bed by simply adding one of these. The other thing you can do with the heat bed is actually increase the wiring. So I've been showing you a few diagrams as we've been going through this video, and I thought I'd take a moment to just step out and explain them to you. So I drew them up in Visio here, and the one we're looking at right now is like an overview. So what we have on the left here is a typical output stage of, say, a RAMPS 1.4. It could also be the MKS board or any other typical low-cost 3D printed controller board, where you have a microcontroller, which I haven't put on the diagram, it's not relevant, sending an on-off signal to a MOSFET, and that signal is going to be going from 0 volts to anywhere between sort of 3.3 to 5 volts ish to try and turn this MOSFET on. This MOSFET, we're using it as a switch, but as I've already explained, it won't always get to this 15 milliohms here, because it requires it to have 10 volts on the gate to guarantee that. So it's probably going to be nearer 20 or even higher in the milliohms. So lots of watts being generated if you've got a lot of current going through it. The typical board, you'll have 12 volts being fed in. In this case, this is representative of the RAMPS board. You've got a 5 amp fuse feeding the steppers and the main board and the Arduino Mega that normally goes underneath it. And then you've got a 12 volts with an 11 amp fuse, which is then being looped through to the connectors for the heat bed. And then the return from the heat bed would come back in through the MOSFET to ground and back to the power supply. So this would normally be your typical 12 volt type of system. Now obviously this can handle 24 volts. There's nothing in here that's going to get damaged with 24 volts, not when you look at it in a simple way, because the FET will handle 60 volts and up to 50 amps. But without a heatsink on here, and when you bump up to 24 volts, instead of running with 10 amps, you're going to run with 20 amps, and now you're going to be having maybe 6, 8, 10 or more watts being dissipated on this MOSFET, and that's going to burn it up without a heatsink. And most of these things don't have a heatsink or have a very small one on this MOSFET. So the MOSFET drivers, the external ones, the black one from Gearbest is this top one here. This is exactly as it is laid out. I actually reverse engineered it a little bit. So we've got the full wave bridge rectifier here, which means that your bed input can be either polarity, it doesn't matter, it corrects itself through this. The 12 volts coming from here gets fed through a 10K resistor and a light emitting diode, and then goes back to it. So very little current is drawn from here, so we don't have to worry if this thing isn't turned fully on. It's going to run cold. This here, the PC817, this is the opto-isolator I was talking about, and it provides several thousand volts of isolation. On the other side, you've got your 24 volts coming in. Could be 12, could be 24, could be a bit more if you wanted. It feeds the opto-isolator through a 10K resistor, and it also feeds through a 100K and LED for letting you know that the output is switching on. When volts are applied to the bed input, a current flows through this light emitting diode inside the opto-isolator. It shines a light on this light sensitive transistor that's inside the package, which again turns on and allows the 24 volts through a 10K to be applied to the gate of this power MOSFET. Now there's also a 10K pulling down to ground, so really when this transistor turns on, it's going to limit this voltage here to about 12 volts, which is still more than enough to turn this thing hard on. There's no current involved here, remember. When this is turned hard on, your 24 volts is going out to your bed, comes back in through the MOSFET into ground and back to your power supply, your 24 volt power supply. Now this side here does not have to have any connections whatsoever to your 12 volt system. Keeps it completely isolated, and that's a lot safer way to do it for a lot of people. Now the red external MOSFET driver I showed you pictures of, I don't have one to fully reverse engineer, but based on the components that I've seen in pictures and things, I'm pretty sure this is a fairly accurate representation of what it is. It doesn't have the full wave rectifier, so you do have to be conscious of the polarity on the input. And it has two inputs, one for a low level microcontroller kind of feed through the 750 ohm resistor, and one that can take a 12 volt signal from the bed output of a controller to feed through to the opto-isolator. So you could use it on either one, not both, but just one or the other. After that, the basic operation here is going to be the same. You're going to turn this transistor on, it's going to feed a voltage down. These two transistors are just going to increase the drive to the gate of the MOSFET. And again, you've got a divider here. They're not quite equal. You've got 36K and 20K, but that's going to still put you about 10 volts on here on the gate if you've got a 24 volts going in. I haven't done the math, but it's going to be roughly that. So you're going to get the same thing. This is going to be turned hard on, and you're going to get your full 24 volts being given to the bed of your 3D printer. Now, a typical wiring, just flip to here, would be you've got your controller. It doesn't matter if it's a RAMPS or some other controller. It's being fed from your 12 volt power supply. There is the bed outputs are going to go into the MOSFET controller. Now I haven't shown all the circuitry here because it doesn't matter. Your 24 volt power supply, you really want one that's probably greater than 20 amps, especially if you're going to be driving a heat bed that has been working on 12 volts and you're going to increase it, like for a larger one. Your 24 volts feeds into your MOSFET board, and then you've got your output to your bed, and that's pretty much it. So this is the modification. What you would have normally without the MOSFET upgrade is you've got your 12 volt power feeding into the controller, and then it's looped out to the bed and comes back and then goes back to the ground of the power supply. What I'm showing you here is a slightly alternate way of wiring it so that you can eliminate the power loss in one of the wires. So if you take 12 volts straight from the power supply to the heat bed and then back from the heat bed into the controller, you need to make sure you get the right side of the controller. It wouldn't be the plus as indicated on the board, it would be the other one, the minus, because you're going through the MOSFET back to ground. This would work nicely as well. If you're not quite sure about what I'm talking about here, then stick with the previous diagram. So that will be this one. All right. I have an alternate wiring method here even for the MOSFET. So this one here is for, you're not going up to 24 volts, you're staying with 12, you're just improving the wiring a bit so that you can get a little bit more power to your heat bed. You can also crank up the volts on your power supply. These are normally 12 volts, but there's usually a little adjustment pot. You can see one here on this particular one. You could probably take that 12 volts up to maybe 13 and a half volts without too much of an issue on your controller board. It wouldn't go too much beyond that, because any regulators are on here will start to run a little bit warmer, but you can get an extra 10% of power or more out to your heat bed, which, couple that with the wiring changes, will give you quicker heat ups and maybe a bit hotter. Put a bit of insulation on the back of your heat bed, that'll help too. An alternate wiring with the MOSFET is similar to what I showed you with the no MOSFET upgrade, where you're staying with 12 volts, is you run the 24 volts straight to the heat bed. Don't go to the MOSFET first. Often this could be as much as a meter or more of wire, and that will give you a lot of dissipation just in the wiring because of these high currents. So it goes straight from the power supply to the heat bed, back from the heat bed through the MOSFET back to ground. You eliminate one complete run of wire, and depending on the printer, that could be a long run. Now the last thing I want to show you here is this little chart. Let me just zoom into that a little bit. This is from an Excel sheet that I put together. These are the internal and external MOSFETs. They're typical on resistance. The voltage drop you would see on them at 20 amps, so 300 millivolts for the one that's built into the RAMPS 1.4 board. And you're going to dissipate about 6 watts here, assuming it's fully turned on. If it's not, it's going to be a lot more. And if you're running at 10 amps, obviously you've got a quarter of that power. Remember, doubling your current or doubling the volts will quadruple the power. Now for wires, I was telling you about upgrading the wires. My Tronxy X5S, for instance, is using 16 gauge wire. So it's rated for about 10 amps when it's actually in a bundle with other wires, which obviously these are because they're all wrapped up and things like that. Has about 13 milliohms per meter, and the volt drop at 20 amps would be 260 millivolts just in the wiring. So remember, we've already got 300 millivolts dropped in the MOSFET if you've got the lower quality one that's built on the board, and then you've got another 260. So now you've got over half a volt gone from your 12 volts just in wiring and switching. Never mind connectors and everything else that you might have where you're losing some power as well. And you're probably going to be losing more than that. Right? So it pays to increase the wire thickness if you can. For instance, going to 12 gauge, which is designed to handle 20 amps. So if you are going to use a low resistance heat bed with a 24 volt supply, then you want to be able to handle the 20 amps. Going to 12 gauge will only drop you 100 millivolts instead of 260. So you've halved, more than halved, the volts drop that you're going to lose in the wiring. But you have to make sure you've got some kind of flexible wire or something, because obviously if the heat bed is moving, that's going to be an issue. Or for instance, in the Tronxy X5S, the heat bed is what goes up and down, so you've got a number of cable chains and things that wire has to snake through. So you want to have it thick to minimize your losses, but you still want to have it flexible. So potentially you could double up on some thinner wires to get there as well. Maybe a couple of 16 gauge or 18 gauge wires, maybe 3 18s or a couple of 16s would do the same job but be more flexible. Obviously at 10 amps is a little different. So be aware, a lot of cheaper printers may not have nice heavy gauge wiring. If you're going to upgrade, you definitely should look at upgrading the wiring for the power side of things anyway. And that's pretty much it. So let's get back to the video and finish off. I just wanted to explain the diagrams as to what I was showing you as we were going through. I think hopefully that now makes it a little clearer to you. So these external MOSFETs are definitely a good idea to have. So let's get back to the video. So now that we've had a look at the wiring diagrams and a few other things, we're not going to do the actual upgrade in this video, but I wanted to just quickly mention about power supplies. I was looking around at various sites for power supplies. Now Gearbest has sent me one. What they've sent me is this one. And as you can see, it's 24 volt, but it's only 15 amps. It's the biggest one they had at the time. Now, if you take a 12 volt, 1.1, 1.2 ohm, let's just say 1.2, keep the math easy again, heat bed, that's a typical resistance for a lot of heat beds that come with a 12 volt system, then that's going to be drawing 10 amps. Right? So when you see these 12 volt systems that say, oh, we've got a 30 amp power supply, that's way, way overkill for what is probably being drawn for it. Nevertheless, if you increase the voltage to 24 volts, that 10 amps is now going to be 20. And as you can imagine, this power supply here is only 15 amps. It is not going to be able to provide enough volts for that heat bed. So we're going to have to dial down the voltage. Usually you get you can probably dial the volts down to say 19 or 20 volts on the power supply, which would help mitigate that. It's also not on all the time, so it still may be able to supply a bit more. But really, if you can, what you want to do is you want to get yourself a 20 or 25 or even 30 amp 24 volt power supply if you want to do the job correctly. Now, because as I mentioned, a lot of the heat beds are wired up with, say, 16 gauge wire. My TiVo Black Widow is using 16 gauge wire, and as you can see from the table here, that is more than enough to cover the current that system is drawing, because the heat bed is about 1.9, almost 2 ohms, which means it's only drawing about 10 amps. Here's the exact figures in this table. If you increase a 12 volt, a predominantly 12 volt bed, or at least one that's running on 12 volts, that's about 1.2 ohms, that's going to go up to 20 amps. That's going to exceed the rating of the wires that are being used, more than likely. And so what you really want to do is also increase the wire size to something like this. This is 12 gauge wire, so it'll take 20 amps or more quite fairly happily. Now it's a little bit stiffer, so what you can do is you can use some thinner wire but double it up so that you've got it more flexible, or try to get some more flexible wire, because remember, this is going to go to the heat bed and it's going through cable chains or something like that, and it's going to be moving around. Now if, like the TiVo Black Widow, it's not going through a cable chain, it's just basically loose behind the bed, that's one thing. This will probably work okay as long as you make sure the ends are well secured. But if you're going to put it on, say, the Tronxy X5S, where there is a cable chain running from the heat bed back to the power supply, then you want to make sure that it's not going to inhibit the movement of the heat bed up on the axis and things like that. Also, what you want to do is try and shorten the length of wire as much as possible. If you look at this table here, you'll see that thin wires have more resistance, which means you can lose a significant amount of power just in the wires. So if you increase from 12 volts to 24 volts, and you put in your MOSFET, oh well and good, but you're now dissipating 4 times the amount of power in the wires if you don't size them properly, if you don't increase their thickness. So if you're using maybe an 18 gauge or a 20 gauge wire, which might have been enough for the 12 volt system, it is not going to be enough for the 24 volt system. You're going to lose a lot of power in those wires, and they're going to get warm. I'll see if I can do a future video and maybe get a thermal camera on and do some examples of what I mean by that. But you lose a lot of power there. So if you can run from the, and I'll show you these in the diagrams, if you can run from the 24 volt power supply directly to the heat bed, not through the controller board, or not even through here, right? There's no reason why you have to bring your 24 volts in here and then out to the heat bed and then back in through the switch and then back to the ground. You could take the power from the power supply directly to the heat bed and eliminate maybe 1/2 meter of wire. Obviously the return has to come back to here, and then it will go back to ground, and you also need the 24 volts coming into here still as well, so that your electronics is going to work on this side. You need some power to drive the gate of the MOSFET and things. Remember, there's an opto-isolator in the way. So it's important that you increase the cable wiring if it's not already heavy gauge wire. You just need to make sure you keep it flexible as well, though. Okay, and a few other things, part of the 24 volt upgrade. The one thing I just want to restate right now, though, before I go, is when you do your 24 volt upgrade for your heat bed, unless you're changing your hot end heater to a 24 volt one, so I've got a 24 volt one here, if you're getting your temperatures well enough for your heater already, then don't turn this one into 24 volts. Be aware that the hot ends are not using the 11 amp fuse. They're using this 5 amp fuse, and that is also driving your stepper motors and everything else. As I said, topic for another conversation, but we will go through it. So just for now, be warned, only do the heat bed, don't do the hot end, unless you really know what you're doing and you know how to modify these boards to suit that, or you're using another external MOSFET for your hot end, and that's obviously a perfectly viable option. Okay, hope you liked that. If you did, give it a thumbs up. If you didn't, well then don't. But I will see you in the next video soon.